motivated by trying to give a different characterization for the hypothesis classes that we see in machine learning, like sparse models and neural networks and so forth. So yeah, so this work is in collaboration with my colleague Siddharth Varman and our PhD student Suprabhat Ghoshal. So a lot of the technical work was carried on by Suprabhat. Okay, so let me first tell you what testing is. So testing is a relaxation of learning in a certain sense. So in learning, in supervised learning, the problem is that you're given examples, x, f, x, where you assume or you're promised that f is an unknown function from some hypothesis class h. Okay, so this hypothesis class could be linear functions or neural networks. And then you want to find an approximation of f with respect to some norm by seeing these examples, and you want to do it efficiently. So in testing, the question is a bit weaker. So instead of being asked to recover an approximation of f, you just want to test whether the f, which is the, so you get examples x, f of x. So this f, whether it is from the hypothesis class or whether it's far from this hypothesis class with respect to some norm. Okay? And so to see that if you have a learner, you can get a tester, just observe that, if you have a learner, you can run your learning algorithm, and in the case that f belongs to h, you will successfully recover some satisfactory f. And in the other case, when this f is far from h, you'll maybe recover, the learning algorithm will maybe spit out something, but typically it's very easy to check whether this f that's returned by the learning example is satisfactory with your examples or not. You can draw a few more examples and check whether it's a satisfactory explanation or not. So in that sense, testing is a weaker version of learning, and in some way, any learner must at least be performing this testing task. So, given the deficit of certain, provable results in machine learning in some context, we wanted to understand this testing question better, so that we could perhaps then go on to understand the learning question. So there are two motivations. Yeah. Right. So this is So this is one approach to testing. We use the learning algorithm. So you would first find f and check whether f is consistent with. If f is close to h or not. You can draw a few more samples and then see whether f is close or not. So there are two motivations. One is, as I said, so you can think of it as a prelude to learning. The other is that typically these testers are based on a different understanding of h. So you characterize h robustly in terms of some combinatorial or geometric condition, and that is the property that you check, that the tester is checking. Okay? So, right. So, property testing as a subject has been studied since the 90s for algebraic properties like membership in various kinds of error correcting codes, graph theoretic properties, expressibility as Boolean formula, but not really that much for continuous hypothesis of continuous function classes. Okay? And right, so this is what we wanted to address in this work. So the exact, in the formal sense, the question that we study is the following. So you're given a set of vectors, y1 through yp. So these are vectors in d dimensions. And we want to distinguish between the following two classes. So the structured case is that there is some matrix A and sparse vectors x1 through xp, such that each of these yi's can be written approximately as axi. And the noisy case is you don't have, so for no dictionary A and choice of case sparse vectors say x1 through xp, this y1 through yp is close to ax1 through axp. Okay? So in other words, for any dictionary matrix A and sparse vectors x1 through xp, your observed y1 through yp is going to be far in some distance notion from ax1 through axp. Okay, does that make sense? Yeah. Yeah, so each yi is, for the purposes of this talk, you can even replace this with exactness. So you can think of the structured case as that each vector yi is exactly a matrix times a k-sparse vector. Okay? And it's the same dictionary matrix A that works for all these p vectors. Yeah. So typically this P is quite large. So P is pretty large. So you want to explain a lot of vectors, a lot of input vectors using a small, right, right. So these are k-sparse vectors. So typically this D is much smaller than M. So you have, you want to explain, oh, sorry, yeah, typically D is much smaller than M. Right, yeah. So, I mean, we want to solve these in the interesting, non-trivial cases when, yeah, I mean, it's not trivially true that everything is in the structured regime. No, I mean, you can think of this as a hypothesis testing problem, but yeah, so the question is how to, I mean, yeah, so we want an efficient tester which solves this hypothesis testing problem, which can distinguish structured inputs which can be explained by sparse representations from things which cannot be. And the goal is to somehow get a characterization of of the input set of vectors y1 through yp, which would allow you to distinguish between these two cases. So yeah, so here there is no real noise model. So I mean, yeah, so the farness is going to encode what I mean by yeah, I mean what I mean by noise. So when the tester is supposed to say no, it should be that y1 through yp is far from ax1 through axp according to some notion of distance, which I'll specify later. Not test. So what I mean by test is I want to distinguish noise from structure. So I want to say whether f is in the hypothesis class or whether f is far from the hypothesis class. So whether f is noise or whether f has some structure which is encoded in this hypothesis class H. Does that make sense? Right. Yeah, each of the vectors is k-sparse. Each x1 through xp is k-sparse. Yeah, f is the, I mean, so the hypothesis class is that, I mean, it's a set of input vectors which can be represented as a matrix times k-sparse vectors. So this is also, I mean, right, so you're trying to test a continuous property of real vectors. And in some sense, I mean, in different kinds of situations, this hypothesis is believed to encode natural inputs. Like you would assume that, so we're trying to sort of separate, say, natural images which have a succinct representation from noise. Okay, and this was in fact exactly the introduction of this question in the scientific literature. So Olshausen and Field in a neuroscience paper, so they wanted to explain early visual processing in the brain. And in that context, they looked at this, this computational problem. So you're given this set of image patches y1 through yp, and you want to learn a dictionary of bases, phi1 through phi m, such that you want to minimize both the distance from I mean, yeah, so this is exactly the matrix vector product I told you about earlier. So you want each yi to be close to this phi a in the sense. So phi is the matrix and a is the ai is the vector. Okay, and you also want to minimize the total number of non-zero entries in these vectors. Okay? So it corresponds essentially to the question that I mentioned, but here they were trying to learn this dictionary, right? And yeah, so this kind of so the sparse coding assumption is widely used in machine learning now to learn natural feature representations for data, and you can think of hierarchical sparse coding as a version of deep learning. All right. So the dictionary learning problem is the question of exactly learning this matrix as well as the sparse vector such that each yi is close to axi. And this question is considered a solved problem in practice, so there are many different heuristics, so alternating minimization, KSVD, among others. And there are rigorous proofs for some of these algorithms, but typically they make assumptions on the dictionary and also on the distribution of the inputs. Okay, so you assume that you want to recover a matrix A which has certain properties. I'll talk more about that later. And then also that the inputs are drawn from some distribution, so they're randomly sampled. And these assumptions are somewhat unsatisfactory. So, I mean, in natural situations, you don't expect the inputs to come from some distribution, maybe, yeah, so there's in some sense arbitrary. And so some of the assumptions on the dictionary has also been brought into question. Okay, so yeah, so just to recap, so our motivation is whether there's a sort of automatic way to estimate the sparsity that's more efficient than learning the sparse representation. And yeah, so this could be useful in a scenario where most of the data set is noise. So you could discard the noisy data sets. But sort of more conceptually, our goal is to come up with a robust characterization of sparsity according to an unknown dictionary. Okay. Yeah, so let me say what our computational model is. So as I said, so you have these inputs, y1 through yp. And these inputs, right, so the computational model I'm assuming is that you access these y1 through yp's by a linear sketch. So you can multiply these vectors by a matrix of your choice. And the question that I investigate in this work is just the number of rows in this sketching matrix. So the dimension onto which you project these input vectors y1 through yp. So one could, again, as David talked about yesterday, one could again talk about also the sparsity of the sketch matrix and the computation time to do this matrix vector product. But and these can be addressed, but I'm not going into that in this talk. Okay? All right. So our contribution is we make a connection between sparsity and a geometric property of these vectors y1 through yp. And so this connection is through this notion called the Gaussian width. Okay? So let me talk about that. Yeah, so one thing is that our theorem also makes an assumption about the dictionary, but it does not make any assumption about the distribution of inputs. So it's not that the inputs y1 through yp, which are coming from some x1 through xp, they could be distributed in some arbitrary fashion. So I am not making any such assumptions, but I am making an assumption on the dictionary, and that is this RIP restricted isometry assumption that any subset of the dictionary matrix with at most k columns is well conditioned. So it's roughly orthogonal. And this RIP assumption is a very common assumption in provable works in machine learning about compressed sensing, sparse regression, sparse coding, and so on. It would be very interesting to weaken this assumption, but yeah, that's an open question. Okay. So our main theorem, this is sort of a screenshot from the paper, so it looks a little complicated, but I'll try to summarize. So, okay, so you have these parameters d, k, m, and p. Okay, so to recall, d is the vector, is the length of the vectors that you're given. K is the sparsity that you're targeting. M is the number of columns in the dictionary matrix. Okay? And p is the number of samples. So you're given p vectors, each of d dimensions. And there's some condition on K and M, which addresses the kinds of questions that Partha talked about, where, yeah, so the problem becomes non-trivial. So the point is that, so there exists a tester with query complexity 1 over epsilon square log of P over delta. So query complexity, again, I just mean the size, the dimension of the space onto which you are projecting the vectors. So this is independent of D and M, and it has the following behavior. So in the good case, in the structured case, when it is, so this capital Y is the matrix which has Y1 through YP as the columns, okay? So in the case when Y does have this decomposition, AX, where A satisfies the RIP assumption and X has each column case sparse, then it is the case that the tester accepts. In the no case, when Y does not admit this so in the no case is a bit more complicated. So this is a far sense. So if it is the case that Y even does not admit a decomposition of the form A x plus Z plus W, where x plus Z is roughly k-sparse and W is roughly small, okay, is small in some sense. So this matrix A is again RIP. The coefficient matrix X is somewhat more than k-sparse, so it's k over epsilon to the 4 sparse. And these matrices Z and W are small in the sense that the Z is small entry-wise, and this W has each column being of small L2 naught. Okay? So the point is that so this is a relaxation of being equal to A times X. So here I'm allowing additional flexibility that X is not exactly k-sparse, but it could be a perturbed version of a sparse set of vectors. And this W is not exactly 0, but it could be small in the sense that every column has small norm. So if Y does not even admit this kind of decomposition, in that sense Y is far from having this decomposition, then the tester rejects. Okay. All right. Yeah, I mean, so this is the soundness condition that we come up with. I mean, it looks a bit complicated, but I mean, it comes as a result of our of the choice of the criterion that we test. Okay? So yeah, so the tester really is actually very simple. So all that it does is that you are given, okay, so we have this notion of Gaussian width. So if you have a set of vectors S, okay, so you can define the width of S to be the largest correlation between any vector in your set and a random Gaussian vector, expected, I mean, the expectation of that over random Gaussian vectors. Okay. So if you pick a random Gaussian vector, what is the most correlated vector with G? So a tester is the following. So you estimate the Gaussian width of the set of vectors. So you have y1 through yp. So you estimate the Gaussian width of that by measuring its correlation, by choosing a few random Gaussian vectors G and measuring their correlation with the given vectors y1 through yp. Okay, so the matrix, the sketch matrix consists of just random Gaussian vectors, and you accept if this width is sufficiently small. So if this width is square root k log m over k. So m again is the size of the dictionary, number of vectors you have in, number of columns you have in the dictionary matrix. Yeah, so just to recap, so what this is saying is that if the set of vectors has a sparse representation, then it has small Gaussian width, and also the other way around, that if it has Gaussian width of this order, then your set of vectors can be written in this form. Okay, so it has a sort of approximately sparse representation. Okay, so just to give you a sense of where this bound is coming from, this square root k log m over k. So these are some well-known facts in convex geometry. So if you have a set of, if you have a finite set S, then its width is bounded by something like square root log S. So I'm hiding constant factors here. If you're, so the smaller the set is, the Gaussian width goes down like this. If the set is of dimension k, then its width is like square root k. And if you have a set of k-sparse vectors in d dimensions, then its width is square root of k log d over k. Okay, and this is what you see here. So, for example, if the dictionary matrix was just the identity matrix, then y1 through yp themselves would be sparse, and then you would expect their Gaussian width to be square root k log d over k. And this sort of roughly also holds when the dictionary is RIP. Okay. So yeah, so Gaussian width of k-sparse unit vectors is square root k log m over k. So this x is a m dimensional vector because A has m elements in the dictionary. There are m elements in the dictionary. And then the point is that, yeah, so you can use standard tools in convex geometry to argue that if A is RIP, then it approximately preserves Gaussian width. Okay? So yeah, just to give you a sense, so we sort of played around, we didn't do a lot of experimentation, but one experiment that we did is with, so we plotted the sparsity versus the Gaussian width for image data. So the sparsity is gotten by by a dictionary learning algorithm, which learns a representation, and so this is the average sparsity. So basically you take a image, you chop it up into patches, and then so each of these patches is one of these yi's, and then you learn a dictionary corresponding to this image. Okay? And this is the average sparsity over the set of patches. So yeah, so I mean roughly you see that the sparsity, I mean the width sort of grows roughly as square root of the sparsity, but I mean there are many other factors here which yeah, maybe average sparsity is also not the best choice, but in any case you see sort of a correlation between sparsity and Gaussian width. So in terms of our result, I mean, so the more interesting case is the other direction. So we want to say that when the Gaussian width is small, then it's also the case that you can approximately, you can have an approximate sparse coating of the set of vectors. Okay, and so let me, in the remaining, how much time do I have? Yes, 15 minutes. Okay, yes. About 5 minutes. Okay. All right. So so let me just sort of wrap up. I mean, yeah. So sort of give you a sketch of the analysis. So I mean, the main point is that this Gaussian width is quite interesting. That it acts as a robust measure of the intrinsic dimensionality of a data set. Right? You sort of saw that even earlier, where I mean, I said that if I have a subspace of dimension k, then its width is like square root k. So in many ways, the square of the Gaussian width is a measure of the intrinsic dimensionality of the data set. So for example, there's this Johnson-Lindenstrauss theorem. I'm not going to go over this, but basically instead of the dimension, you can, yeah, so you have the square of the Gaussian width up here. Okay. So yeah, so our soundness analysis is basically this. So you have some set of vectors y1 through yp, and they have Gaussian width. So the tester has made sure that the Gaussian width is square root of k log m over k. And now I want to prove to you that this means that y1 through yp has an approximately sparse representation. Okay, so we will show that S is close to an incoherent linear map applied to, or an RIP linear map applied to theta k sparse vectors in m dimensions. All right. So there are two cases to this analysis. One is when the intrinsic dimension of the vectors is low, and when the intrinsic dimension of the vectors is high. Okay. So in the no case, when omega of s is less than epsilon square root of d, there's this lemma, which is again a manifestation of a phenomenon that David talked about yesterday in his talk. So if you have a set of vectors which has low Gaussian width, so think of it as having low dimension, then if you randomly rotate the vector, you can make sure that all its entries are small. Okay, so with probability at least half for a randomly chosen rotation, the infinity norm of y, where y is yeah, so basically you have this set S, which has the Gaussian width omega s. You can make sure that for all the vectors in S, their largest entry is small. Okay, and yeah, so in this case, so in the case when omega of s is less than square root of epsilon square root of d, this is say less than epsilon. So that means that in fact y can be written as some rotation times some z, where all the entries of z are small. Okay, so in that sense, so it falls into the sort of the other case. So in the main theorem, if you remember, there's this case where y equal to ax plus z plus w. So this is sort of the trivial case when x is 0, but you can write your vectors as a times some vectors which are small infinity normwise. Okay. So the other case is the more interesting case when the vectors are of high intrinsic dimension. So just by a choice of parameters, you can. This means that d, the dimension of the input dimension, is something like k order k over epsilon squared times log factors. So this is the key lemma in our work. So we show that if D is small, okay, so D is of this order, and you take a random Gaussian matrix phi, okay, then you can cover the unit sphere in D dimensions by taking L sparse, so L is some order K, okay? So you can take sparse vectors in M dimensions and project them down to D dimensions. Okay? Does that make sense? So so you can cover all of the unit sphere in D dimensions by incoherent map or a RIP map applied to sparse vectors. So our set, was inside this, right? So, okay, so there is some normalization I'm not telling you about. So this phi of SL may not be unit vector, so you need to normalize it, but it's not a very important matter. So what happens is that so essentially you can write your set X, which are the input vectors, as you can write each of the yi's as being close to phi of xi, where close means that you have this order epsilon to the 1/4, which is coming from the fact that this forms an order epsilon to the 1/4 cover. In one slide why this lemma is true. So it's just, so you use Gaussian width again, okay? And the point is that if a set of unit vectors has high Gaussian width, so now we are using sort of the flip side. So if a set of unit vectors has high Gaussian width, then for a random rotation, you can rotate this set T so that it becomes a cover of the whole ball. So again, high Gaussian width means that its sort of intrinsic dimension is close to n. So you'd expect it to be sort of to fully span the n dimensions, and we can prove that this implies that you have a cover of the unit ball. Yeah, so you basically use this fact along with a lower bound on the Gaussian width of L sparse vectors in order to prove the Key Lemma. Okay. So in summary, so what we did was we obtained a robust geometric characterization of sparse coding, and that allowed us to get a fast and robust distinguisher between sparse and non-sparse sets of vectors with respect to an unknown dictionary. So I believe this pursuit is very interesting. So currently we are looking at, say, neural networks with one hidden layer, and we would like to give a geometric understanding. So it's more complicated than just that its Gaussian width is small. Sort of a different kind of understanding of what it means for a set of vectors to be represented by a neural network with one hidden layer. With bounds on the weight vectors. Okay, so yeah, it's interesting to extend this to other hypothesis class in machine learning as well. Thank you. Right. But then the fact is, so then you need M to be as big as P. You need a huge number of, the dictionary size would have to be very large if you want to have just this trivial representation. But here P could be much larger than M, and you would still want. Right. Yeah, I showed in the other sense that if the Gaussian width is small, then you do have an approximately sparse representation. Yeah, actually you do with a few and use Gaussian concentration to say that the Gaussian width is small. So the algorithm just verifies whether the Gaussian width is small or not. So in the case when they are sparse, the Gaussian width is going to be small, and also if the Gaussian width is small, then there is an approximately sparse representation. Yeah, so the random rotation is also RIP, so you can sort of put it together with. Sorry, I can't hear you. So you're talking about here, right? So what's the question? If you have large Gaussian width, then this says that random rotation is going to rotate it into a cover. Without the rotation, I don't know how to prove. Yeah. Well, yeah. Yeah. Well, I mean, okay, so shouldn't probably take too much away from that. But the point is that, yeah, so we wanted to see whether in for real images also, sort of the Gaussian width captures the complexity of the image. And sparsity as recovered by sparse coding, I mean, the dictionary learning algorithm sort of gives you the complexity of the image. And you do roughly see that the Gaussian width tracks that. That as the image becomes more complex, you get the Gaussian width increases.